All right, cool. So today is going to be session 7 of the ML Scalability and Performance Reading Group. Glad everybody could make it. Today we're going to go over DeepSeek V3, which is a paper I've been very excited to get to. Lots of interesting stuff in it. One forewarning is that there's a ton of content, so we're not going to have time to do like a super deep dive into everything. I'm going to only cover certain aspects that are like most relevant for performance and yeah, I'm gonna have to move really quickly. So I will try to stop for questions or comments occasionally. Feel free to chime in if you want, but I'm gonna try to move fast. So yeah, with that, let's go ahead and get started. Basically, the plan is, infrastructure. All this like systems layer engineering work they did is going to be the primary focus. But first, I wanted to start with an overview of some of the architecture because there's some kind of unique changes that were made that have performance implications, and then I kind of wanted to understand what is the architecture that we are actually training and serving before we start talking about the actual infrastructure and things like that. So let's go and get started. I guess we can go down to where it starts the architecture section. So as everybody might have heard, one of the first kind of key architectural innovations in DeepSeek, actually introduced in DeepSeek V2, is the multi-head latent attention. This, I think, is best illustrated actually in the V2 paper, so I'm going to hop over to that. They have like a better diagram and kind of a more detailed explanation. Basically, the key idea is that rather than, storing the full K and V values for every single head during inference, they actually just have this compressed latent KV vector, which is the only thing actually cached and stored in the KV cache during inference. And they use this single compressed latent vector to perform an up projection using an up projection matrix for keys to get your keys, and then your up projection value matrix to get your full values that are then used to compute your actual attention outputs, right? So you can basically only cache this much smaller compressed latent KV vector and then derive the full larger keys and values that you need to actually compute your attention scores. And this has a huge impact on the size of the KV cache. And also, they actually interestingly claim, this kind of shocked me, in V2 anyways, they claim that the actual model performance was actually superior than just standard multi-head attention. In V3, they kind of walked that claim back. I mean, not walked it back. They just said it's comparable to multi-head attention in V3, but in V2, they straight up said it's stronger performance, which I thought was interesting. But anyways, just to take a closer look at like what this means, they call it specifically low-rank key value joint compression. So in these formulas here, HT is our input token, and coming into our attention layer, and then we have this down projection matrix, which will project it to this lower dimensional latent KV vector. And this, the compressed KV vector later can be up projected with this UK matrix to get our keys for that token. And then same latent KV vector can be up projected with UV to get our values, right? And this, as I mentioned, during inference, MLA only needs to cache this latent KV vector, so big memory savings there. And this other interesting part is that basically they note that in the math, if you're excluding rope in the positional embeddings, basically you can combine, like if you look at the formula here, like say we want to first compute our raw scores, doing our Q and K right here, we're going to have our Q. We first need to up project from the compressed KV vector up to get our full keys using the up projection matrix, and then we're going to multiply to get our actual scores, QK, right? But they note that this right here, the Q and the UK, can actually be combined and pre-computed into just one. They call it being absorbed, like the UK can be absorbed into WQ, and you can essentially just now have one operation instead of two. So you can just have this WQK, is what I called it, by your compressed KV latent vector here, and you actually skip computing the keys directly. You can just compute the scores directly, right? You don't need to have this intermediate step of up projecting to get your keys and then multiply to get your scores with the Q. You just directly apply the compressed KV vector to this combined matrix and you get your scores directly. Very interesting. And this works because, the up projection matrix is not specific to each token. So as you perform, inference, each new token is appended to your context as you go. So this new, compressed latent vector here, you see it's specific to h of t. T is the token that we are currently at. Um, this may be new, but this, for a given query we're comparing with and computing an affinity score with, this is the same, right? The UK is not changed, the Q is not changed, so you just have this pre-computed value. However, so that's cool. They can perform that optimization there. However, I should also note they do the same thing for the UV and the O, same exact concept, but just the up projection for the values, and then we do our output projection can be absorbed. Cool. It gets complicated now when we start talking about rope, because in this part I found like pretty complicated, and I would love feel free to either confirm my understanding or correct my understanding if I miss something or I'm mistaken. Would really appreciate that because this is pretty tricky. My understanding is that basically when rope comes into the mix, the rope rotational matrix is position sensitive, right? So if you look here, we have these position dependent rotational matrix applied to both our Q and our K. And then now this absorption that we looked at up here no longer applies, right? Because now between the Q and the K here, the Q and the up projection of the K, this new rope the position dependent rope matrix is in between them, right? And this position dependent means that with every new KV or compressed like C to the KV here that comes in and is appended to our context, it's going to be different now for that new pairwise comparison, like score that we're computing, affinity between the current token and the some previous token, right? So this is in between them now, and basically like it's not like reusable now. Like the position has changed, and they note that essentially the matrix multiplication does not have the commutative law like regular integer multiplication. So you have to recompute the whole prefix essentially because of the use of rope. So you're unable to do the absorption because you'll have to recompute the full prefix. So what they do is basically something pretty crazy. I mean, it makes sense, I guess, but they just try to decouple the positional information from the context-aware information in the queries and the keys. So they have a separate matrix. So you have your compressed query here, right? The latent query vector. And then instead of doing up projection and then applying rope, right? Because then we'll have that problem. They have a separate matrix and then apply rope to get this first QR, where QR holds the positional information. And then they do the same thing for the key. So they do this input token, then this separate decoupled projection that then they can have the right dimensions and so that they can apply rope. And then now they concatenate those to the previously computed QC and KC, which are the regular up projections that we computed up here. So here's KC, right? So this is basically the way I think about this is like this will have the context aware information, and this will be used for the positional information. They concatenate them together, and that allows them to basically not have to recompute the entire prefix because the rope matrix, the position aware part, is not in the way anymore of this absorption. So yeah, pretty weird. If I'm incorrect about this, please, I'll pause for a second. If anybody wants to jump in and add anything, please do. That's my current understanding though, but this is probably, of everything we're going to talk about today, this was probably the most tricky for me. So please feel free. Okay, sounds like I got it 100%. Awesome. Okay, so moving on. This is the first kind of unique architectural aspect of these innovations they did to greatly reduce by 95% the size of the KV cache with this MLA variant of attention, and they made it work even with rope by doing this decoupling, right? Cool. That's part one. Part two is the MOE. So here we go. So for the MOE, the way we think about MOE is instead of having an attention layer that then just goes through a feed-forward layer, and that's our, how it works, we basically have a bunch of feed-forward layers that may be smaller, or but basically they are sparsely activated, meaning that we route tokens from the attention output to different experts depending on computed affinity scores with those experts. And those experts might be, they might learn some kind of more specialized representation or, um, you know, yeah, some specialization, and there'll be differences between them. And so if we look at the math here, basically what this is saying is for UT, which is our kind of like input token coming from the attention output, first they unconditionally go through some set of shared experts, right? So each expert has like a feed forward layer basically, and it's basically saying we have some set of shared experts where this will reduce the amount of redundant learning that needs to be happen. If there's some like base layer of representational knowledge or transformations that needs to be happened to be useful in this layer, we can share that between all experts. But then for the more specialized experts, we choose via some routing which ones we want to route the tokens to. And basically how we do that is, let's go to the bottom here. Let's start from the bottom. SI of t means for a given expert and a given token, the affinity score, S is the affinity score, is going to be the output of the attention layer for that token, and some affinity score is computed with this. I believe this is like a vector that is used to compute an affinity score of, like, it represents that expert and can be used to compute an affinity score between a token and that expert. And then we apply sigmoids, we get a value between 0 and 1. Then for this value, right, this is the affinity score, we are going to select the top k from the number of routed experts. We're going to select the of all the computed affinity scores, we're going to select the top k affinity scores, and then we can use these affinity scores. So it's 0 if it's not part of the top k, or it's just you keep the affinity score if it is part of the top k. Then we can compute a gating term or a gating factor, which basically is just like the weight that we apply to that expert's output based on that affinity score divided by the sum of all the affinity scores, basically. So it's like how much weight should we give this expert's transformation on the token, right? Because the FFN will do like up projection, then down projection back to the original dimension of the token. And again, we're recombining all of the outputs of the shared experts and the routed experts to finally get our updated H of t, which is our updated token based on all the updates, the weighted updates of all the experts that we routed to, including the shared ones. Cool. Okay, so that's kind of the architecture. There's some other kind of pieces of the architecture that are actually sort of not really. This is kind of interesting. I actually hadn't seen this done before. They're adding auxiliary losses. So this is still part of the model architecture, not like systems layer engineering. They're adding auxiliary losses that are not going to affect the actual numerical properties of the model outputs, but are going to affect how the computation that occurs to get those outputs is performed. So specifically, they do a couple things. So before we get to this, we actually need to talk. Oh man, why did I do that? So they do something called auxiliary loss-free load balancing. But the reason why that's even notable and why they mention it at all, if I can find where we were, there we are, is because in V2, they do something called, they do use auxiliary loss for load balancing, right? So they have multiple auxiliary loss functions to ensure A, the computational load across experts is balanced, because as they note here, if there's an unbalanced load across experts, there'll be something called routing collapse, and it will hurt our computational efficiency, okay, when we're doing expert parallelism. And they minimized this previously by using this auxiliary loss function. Now what they do is, but basically, so they noted that basically the auxiliary loss function can impair the actual model performance, like the model quality of its outputs, because you want your loss think to be focused on really the quality of the output tokens and not just being impacted too heavily by what computational pattern was used to produce those outputs. And so instead, what they do is rather than having this new loss function, they introduce this bias term to the affinity score between a token and an expert. And this bias term is not a learnable parameter, which is very important. It is a hyperparameter which is dynamically adjusted at the end of each training step based on if the corresponding expert I is overloaded, and they increase it if it's underloaded and decrease it if it's underloaded. So they're manually adding a bias, playing with the affinity scores for each expert based on how much load that expert has been dealing with, right? Which is they do a lot of this stuff in this paper with this like dynamically like modifying the computational patterns. It's pretty crazy. So we'll see more of that. Moving on, they do use one auxiliary loss though. So this is auxiliary free load balancing for across experts, but within a sequence, they use an auxiliary loss just to ensure that with the tokens within the sequence have like some prevent an extreme imbalance of how they're routed. They also use node limited routing, which they discuss here. Whoops, I think it's up here. Basically, this is complicated, but basically they say they try to select. So for each token, when doing the routing, right, of tokens to experts, they first select M devices that have experts with the highest affinity scores in them, right? So the experts are located somewhere, and they select those devices and perform top K selection among experts on those M devices. So what they're trying to do here, I believe, is avoid sending too much data over InfiniBand, just like internode communication, basically. And they're trying to send, say, like one token. If you know like multiple of your top K experts are on this device, you can send that one token there over InfiniBand and then forward it over NVLink internally on that node to multiple experts. Where there's much higher network bandwidth and you can afford to do it, basically. So they're trying to route tokens to nodes where there's a high density of top K experts, I believe, is what they're doing. So pretty interesting. And they're really going like above and beyond here. Like this is my whole thing. Like we'll keep going, but they're doing a lot of things that I think just in prior papers we've looked at, like they were just kind of ignored or just viewed as like unavoidable overhead of like internode communication and stuff. Yeah, anyway, so another thing here, they're doing multi-token prediction. So computing multiple token outputs at once instead of just one at a time in autoregressive decoding. Full transparency, I did not have time to do like a deep dive on this and like look at the prior work and stuff. So I'm not going to spend a lot of time on this. I just had a crazy week at work and couldn't look at these. But just from reading this section, which provides like a brief kind of introduction and overview, they say that it helps densify the training signals and improves data efficiency, and it also enables the model to kind of pre-plan representations for better predictions on future tokens. So they can have like a causal chain or keep the causal chain at each prediction depth. So there seems to be some. I thought it was just when I first learned about this, I thought it was just an efficiency benefit rather than having to sequentially predict each token one at a time. I expected that if you could predict like 4 at a time or whatever the number is, you would just be getting a performance improvement in terms of like utilization and like total tokens per second generated. But actually, they said that there can be some model performance improvements as well due to the reasons I talked about here, like pre-planning the representations for prediction of future tokens. So this is something I would look more into because this really surprised me, and I think that's really interesting. But yeah, moving on, got to keep moving. Lots to cover. Finally, now we have the context. We've talked about the MLA and how they basically the two aspects of the architecture that are kind of relevant for all the rest of this, the MLA, the MOE, some of the auxiliary loss, and smart token routing that they're doing. So now we can talk about the infrastructure section and the systems layer stuff. So they talk about the hardware they used, which is they used the H800 GPUs famously. They claim that that they're just using H100s, which are not as high end as like H100s. They're a pretty standard setup where internode communications over InfiniBand, and then intranode has NVLink and NVSwitch within the node for higher network bandwidth, lower latency. Next, as they get into the actual like training framework and types of parallelism they apply, basically they're applying 16-way pipeline parallel, 64-way expert parallel, spanning 8 nodes, so I guess 8 experts per node, and then just 0, 1 DP. So I think 0, 1 was the optimizer state being partitioned, if I remember correctly. Feel free to correct me, but yeah, so they're doing this like 3D parallelism, and what they do is implement their own they developed this pipeline schedule called dual pipe, and it builds on what we looked at last week, which is zero bubble pipeline parallelism. And we'll kind of look at that in more detail. And kind of what they claim here is that they don't have to use tensor parallelism, which is pretty costly due to everything else they're doing. It's just not necessary. So let's keep going and look at dual pipe. So basically, okay, when they're partitioning the model into different chunks or stages along the pipeline parallel dimension, what they're doing is dividing into 4 components: the attention, then the all-to-all dispatch of the tokens, right, to different experts, then the actual MLP, which is like the actual expert, computation. It's like producing the output for that expert, and then the all-to-all combine of the expert outputs, right? So these are communication, and these are computation. Then for the backward, they're doing something very similar to zero bubble, which is for the attention and MLP layers. For the backward pass, they split it into 2 parts, which is computing the gradient with respect to the input and the gradient with respect to the weights. And as we noted in zero bubble, this is done because the gradient with respect to the input is blocking and a necessary step to continue backprop to the previous layer. The gradient with respect to the weight is not blocking for backprop. You can asynchronously kind of compute that or schedule it later to fill bubbles in the pipeline. So that's one thing that was kind of this higher granularity implementation of the backward pass is something introduced in zero bubble that they use. And then they also do something kind of interesting, which is they do bidirectional pipeline scheduling, which means that rather than just feeding in microbatches from, if we look at the diagram at the bottom here, instead of just feeding in microbatches at device 0, and then, most pipeline parallel schedules you see do start like that, and it fills up and reaches some sort of steady state. They actually start from both sides. So they start from 0 and 7, and they're feeding him from 2 devices. They're feeding microbatches in 2 devices at once and moving those microbatches opposite directions across the pipeline. So from 0 to 1 to 2 to 3 to 4, and from 7 to 6 to 5 to 4, and so on. And this helps achieve a lower pipeline bubble and better computation to communication ratio. So pretty interesting. This you can see they compare to 1F1B, which is standard 141 backward, zero bubble, and then theirs. And they say that the bubble is smaller, but it does come at the cost of higher parameter counts. By that, what I mean is that since we're doing 2 microbatches at once, like we are feeding in from 2 directions at once. I believe, this is my understanding, correct me if I'm wrong, but I believe since we're feeding microbatches in 2 directions at once, we have to save 2 copies of the model parameter. So it says dual pipe requires 2 copies of the model parameters, but because they're partitioning across high expert parallelism size, 2 copies of the model parameters, but then you divide by 64 expert parallelism dimension, it's not hugely significant, is my understanding. So that's kind of one innovation they did, building on top of zero bubble, getting some incremental improvement there. Next, they talk about their implementation of cross-node all-to-all communication. This is just kind of talking about what I was talking about earlier, how they just go into more detail here, basically explaining how they route. We limit each token to dispatch to 4 nodes, reducing IB traffic. And then, once it gets to that node, it can be routed to the experts within the node over NVLink. So, just basically trying to find some balance point where you're reaching all the experts, but you're picking the nodes that have the most top K experts on them, and that way you can, minimize the number of bytes that are sent over InfiniBand, and then the kind of fan out once it reaches the node over NVLink will be done over NVLink to the different experts. So they kind of just talk about that in more detail here, and they claim that basically using this strategy, only 20 SMs are needed to be dedicated to communication to fully utilize the bandwidth of InfiniBand and NVLink. I believe this is out of 132, so they're keeping the vast majority for computation. And then they also use something called warp specialization, which basically means different warps can be specifically tasked with one role, like receiving data during the all-to-all like combine from the expert outputs, right? There can be warps specialized for that, or some warps specialized in sending data at the end of the like expert computation, sending the outputs out to other nodes. And then basically they say, so this is during the dispatching process. There's 3 stages, right? Sending over IB to NVLink forwarding, and then NVLink receiving. These are all handled by respective warps, and this number is dynamically adjusted according to actual workload across all SMs. So this is, again, another instance of dynamically adjusting the characteristics of the actual computation and communication that is occurring depending on workload, and not just relying on the compiler to like hopefully make good decisions, and then looking at the profile of your traces and your communication and trying to overlap them more. It's actually algorithmically handling that at runtime, which is interesting. And then, they do it during the combining process as well. So dispatching tokens to different experts, combining outputs of experts to get the final updated token representation. So this is just like the reverse, NVLink to IB, and then IB accumulation, also dynamically adjusted. Also, they note here they employ custom PTX to auto-tune communication chunk size. So PTX is basically the assembly of CUDA. And so they're like handwriting PTX to dynamically auto-tune communication chunk size, which I guess they're probably doing because it's not well supported in the software abstractions provided by CUDA. And this reduces the use of the shared L2 cache. Remember, L2 cache is shared across SMs. And so it lowers the amount of interference with the SMs performing computation. So this is one thing I just want to note here. A lot of times we read these papers and they're talking about overlapping communication and computation as if they're like fully async separate systems that have no interference with each other whatsoever. But really, it's not free. Like when you still have to dedicate computational resources to perform the communication, sending and receiving, moving data between InfiniBand and NVLink, etc. Those are SMs that could have been used for computation. So there's some amount of cost there. And then also, there's like shared L2 cache. And so, the more devices that are utilizing the L2 cache, there can be some interference and just less availability for each one if more are using it. So, minimizing the impact of the communication kernels on the L2 cache is better for the computation kernels, which will make better use of the L2 cache. Okay, moving on. Now I talk about more memory saving optimization. So the first one is kind of obvious, which is that they don't save the MLA up projection, they recompute it. And this is during training, so this is not like one of the inference benefits of MLA, but this is a training benefit, which is that your activations you are saving, or rather your benefits of activation checkpointing, meaning that just keeping the compressed KV vectors, the latent vectors, and not saving the intermediate activations, the up projected Ks and Vs, saves memory as part of like an activation checkpointing strategy. They also use AC on the RSM norm and recompute it. I was interested, this is such a brief section, I was curious. They didn't do any comparisons with like, there's a lot of different AC settings like full AC, per layer AC, per op AC. It seems like they just state, we're using it on these two and then move on. There's not really any like comparison on like throughput or anything like that. So yeah, I was a little curious about that. But moving on, exponential moving average. So this is just something people use to predict future like model performance towards the end of training. Early on in the training process, they can predict it by tracking these exponential moving average parameters, and this allows researchers to like quickly detect if like, okay, this is not going to be a good experiment and like end it and then try something else. But they store it in CPU and update it asynchronously. Just another optimization there. Shared embedding and output head. This is, I found weird. Basically, they're saying they deploy the shallowest layers, like the embedding layer, and deepest layers, the output head, of the same model in the same pipeline parallel rank. This enables the physical sharing of parameters and gradients and the shared embeddings in the output head. I find this a little confusing. I talked to some people about this. My understanding is basically the input embedding transforming from the input vocabulary space to the embedding dimension, and then the output layer, which will transform from the embedding dimension back to the vocabulary space, are like inverses of each other and can technically be done with like the same tensor, and therefore you would have the same parameters, same gradients, and so on. That's my understanding. It's just like another optimization. I could be wrong about this. I find the way they phrase this like kind of weird, but that's my understanding. FP8 training, this is pretty interesting because FP8 training is getting a lot of steam right now. So basically, this is a form of low precision training that has performance benefits. Specifically, what they're talking about here is some of the ways they worked around some of the challenges in low precision training, which is namely that it's very sensitive to outliers, particularly in things like activations, which will have more outliers, like more extreme outliers. So what I mean by that is basically to scale a set of high precision inputs in a tensor to a low precision tensor like FP8. So you see you have a BF16 tensor in your activations and you want to scale it and transform it to a FP8 tensor. You have a lower range of values that are representable in FP8. You have fewer exponent bits and fewer mantissa bits, which is like the fraction after the decimal. So what you need to do, and what is normally done, to find a scaling factor which you can apply to the BF16 values to scale them to a range that is fully bound within the representable range of FP8. They find the absolute maximum value in the BF16 tensor, right? So the largest absolute maximum value in the BF16 tensor, just restating, and then you take your the maximum value representable in, I can write this down really quick too. Here we go. Basically, oh my God. Here we go. So we do FP8 max representable value, and I'll make this larger, and then divided by tensor BF16 Amax, right? Your absolute maximum value. So basically what you're finding is you're mapping the largest value in the tensor to the largest representable value in FP8, right? And then you apply the same scale to all values in the tensor. So everything by definition will come within the representable range of FP8, right? Because you mapped the maximum value that exists in that tensor to the largest representable one in FP8. And so everything else will come in between that, right? So the problem with this is that if the larger the surface area of this computation is, if you're looking at the whole tensor, when you're computing the absolute maximum value of the whole tensor, that could have 4096 times 4096 elements. It could be millions and millions and millions or however many elements. if, your chance of seeing one outlier value that's like extremely large is much higher. And then now suddenly all of your values are getting scaled by this huge amount. So even though 99.999% of your values might fall between like 0 and 1 or like -1 and 1 or something, just because you had one weird value that was like 10,000 or something, now suddenly you're hugely compressing all of these values, and you're not utilizing your range that FP8 can represent well at all. And this will have bad effects on the actual like the numerical stability, the actual model performance. Like when you finish training, it can fail to converge properly, and so on. There's things like that. So what people do and what they are doing is two things. They basically reduce the they're basically doing the grouping to compute the scaling factor at a smaller scale. So rather than using what is called tensor-wise dynamic scaling, which is what I described here, finding the Amax across the entire tensor, they're finding the Amax only across one channel here, right? Like one on the row dimension and NC on the column dimension. So it's like one vector basically, and you compute the Amax for each of those individually in the tensor and apply them, or blockwise. So you find like one like rectangle or block here. And you compute the scaling factors on an individual block or channel level so that if there's an outlier somewhere, only that one subset of values is affected by that, and the vast majority are not, which reduces your quantization error, basically. And so yeah, that's what they're doing, and that's kind of what they're describing here. They also, so that's one thing that they're doing with the FP8 training is, I believe they're using the channel-wise scaling factor for activations, and then block-wise for weights and gradients, if I remember correctly. The other thing they're doing, so that's one thing. The other thing they're doing is something pretty tricky and crazy, which requires like probably like custom PTX or something to be written. But in the FP8 gem, so gems are general matrix multiplications. In the actual tensor cores on the hardware, you remember when we compute a matrix multiplication, we're going to be performing dot products between vectors, right? So at each step, we're going to be taking, like if you just think about it as if we did it sequentially, right? Just for illustration purposes, we take a product of two values, okay? And then we move to the next index on the row and the column, take the product of that and accumulate it with the last product, move to the next one, product, accumulate it with the sum so far, right? You're taking products and accumulating them, product and accumulate them. And this accumulation is actually, so what they want is that they want it to be done in high precision. So you want the actual products, like all these mammals, or the products to be done in FP8, but the accumulation to be occurring in higher precision, because basically as you add tons and tons of these numbers together, you'll be losing some amount of as basically the how do you say, like the rounding or the error that is inevitable due to using this lower precision value. You're accumulating a ton of that when you're adding all of these FP8 products together, and you're doing it thousands and thousands of times, and that can affect the quality of the outputs of this gem operation and the quantization error thereof. So basically, what they want to do is perform the accumulation step in higher precision, like BF16 or FP32. And what they say is basically that they did some experiments and found that, I think they say it down here somewhere. Yeah, here it is. They found that the accumulation step on the actual FP8 gem in the hardware is only retaining around 14 bits, and they want to accumulate it in FP32. So what they have to do is offload the accumulation step. So the actual accumulation will occur on a separate register and a CUDA core outside of the tensor core. Did they have a diagram for this? Yeah, here it is. So here on the right here you can see low precision accumulation, but then every k intervals. So they do product sum, product sum, product sum, product sum k times. But then after k times of doing that, they move that value off the tensor core to a regular CUDA core where they have an FP32 register available, and then go back and they do product sum, product sum, product sum, product sum, and FP8 again, and then after k of those, move it and accumulate again in the FP32. And that way they're getting, they were able to retain some precision in these accumulations, and they see better performance like that. This is not the way the hardware is supposed to be used. I think they had to hack around this in a pretty hardcore way. I don't know, exactly how they did it, but yeah, that's kind of what they're doing here for the higher precision accumulation during FP8 gems. So hopefully that makes sense. It's pretty complicated, but let's see if there's anything else to talk about here. Let's see. I think that's basically the main things for the FP8 changes they did: the channel-wise and block-wise scaling factors, and then the higher precision accumulation using the FP32 register and the tensor core, or the CUDA core rather. Now, one other thing they did that's becoming popular is use E4M3 for FP8 everywhere, rather than what was traditionally proposed in the original paper for FP8. Like, they proposed using E4M3, which is 4-bit exponent and 3-bit mantissa, for forward pass, and then in the backward pass for the gradients, use E5M2. So that means you have a higher range but lower precision, because the thought was for gradients, really it's the range that matters more. Which, like, the magnitude of the gradient that matters more than the precision and the difference between those magnitudes. But basically, they claim that they can simplify this and use E4M3 everywhere, and it's feasible and achieves like the same performance because they have this more fine-grained quantization strategy, the tile and blockwise scaling factors I talked about. So that's one thing they do. Another thing is dynamic scaling. So this is what I was talking about earlier. Previously there was also there's something called delayed quantization, which means that they basically track some values over some number of iterations and then compute the scaling factor based on like the historical values. So you can see delayed quantization maintains a history of maximum absolute values across prior iterations and infer the current value. But they simplify and just basically calculate it per tensor directly, dynamically, and they say that they can do this because let's see. Yeah, they don't really say. I think they just basically just state they're doing online quantization, like they're doing it dynamically. They're not using delayed scaling. And this is also a trend in the industry in general. I believe that people have just moved away from delayed scaling. It's a lot more complicated to implement, and seemingly the performance benefits are not there to justify it. So I think they're just kind of doing the same thing as others. Low precision storage and communication. There's three things here: low precision optimizer states, low precision activations, and low precision communication. So for the optimizer states, this is actually a particularly interesting one because I talked to somebody who has a lot more experience with optimizer research than me, and they stated that it's actually very challenging and is not widely done to keep optimizer states, like for Atom. We have our first and second moments, these two parameters, to keep them in BF16, because apparently they're very sensitive to precision, and people just traditionally keep them in like FP32 or yeah. So they were actually surprised. The DeepSeek team claims that they can use BF16 for the optimizer states, and they're able to achieve good results still. So I don't know. I was surprised by that. They still keep the master weights and gradients though in FP32, like in normal mixed precision training. Low precision activation. Yeah, this is just talking about how since they're doing the backward pass with respect to the weight and the gradient with respect to the weight in FP8, they can actually then cache the activations in FP8 and avoid doing an extra conversion there from BF16 to FP8. But they have to. Oh yeah, this was really weird. They did something special here. They adopted a customized E5 M6 data format, so 5 bits of exponent, 6 bits of mantissa, exclusively for the activations after the inputs of the linear after the attention operator. They have such little information here. Like, I don't know. I found that kind of strange. They also use the power of 2 scaling factors, which is done commonly with FP8. Or I don't know if it's just FP8, but basically, when we're going to be dividing and multiplying by these scaling factors a lot, and we're using binary representations obviously because it's a computer, and when you're dividing by odd numbers, there can be some rounding involved. You can't just use like bit shifting directly to divide by 2 or multiply by 2. So they round down to the nearest power of 2. And yeah, I didn't really quite understand this part. It's just like to further reduce memory costs, we cache the input to the Swiggloo operator and recompute its output. This just sounds like activation checkpointing to me, like another form of just like recomputing and to reduce your peak memory during training, which is fine. Low precision communication. Yeah, so basically, I believe what they're talking about here is just quantizing the values that are going to be dispatched to different experts into FP8, and that way less data is sent over the network, as opposed to if it was BF16, it'd be like twice as many bytes. I believe that's what's happening. Pre-filling and decoding, for time's sake, I'm going to move over. They just talk about like their actual deployment setup for inference. And communication hardware. This was kind of interesting. So they basically are making recommendations to hardware. I think this is the part. Yeah, they're making recommendations on to NVIDIA and like other hardware vendors based on their points of friction they encountered when trying to make these optimizations. They recommend some sort of unified interface so that there's not so much complications in terms of trying to interact with, there's like InfiniBand, and NVLink, and maybe like different interfaces for sending data over each of them. And it'd be easier if there was like a unified interface with just basic communication primitives. So that's one suggestion they have. The big one, here we go, higher FP8 gem accumulation precision in tensor cores. So they just talked about what I talked about, how they found it's only keeping the highest 14 bits of mantissa, and it truncates any bits exceeding this range during accumulation, and this has negative effects, and so they would like higher precision accumulation supported during FP8 gems in tensor cores. They talked also about how the actual gem implementation, so like when you call into these libraries like Cutlass, that offer like highly optimized gems, like matrix multiplication implementations for different data types. They don't support, at least at the time, they did not support per like row-wise scaling factors or block-wise scaling factors. They only supported tensor-wise scaling factors. And now, actually, I believe this is no longer true. I think Cutlass 3.7 supports block-wise gems now, like block-wise scaling factors. This was just in January that was released, though, so I think that was after this paper was written. Online quantization, yeah, basically, so what they're saying here is that, like, in the forward pass, they have to do a conversion to FP8 with scaling factors on, like, basically row-wise scaling factors become column-wise scaling factors in the backward pass, I think, because the matrix is transposed, and it requires an extra data shuffling over to HBM and back, because because, as they're saying, so we can just read it. We need to read BF16 activation values, the output of the previous computation from HBM for quantization, and then the quantized FP8 values are then written back to HBM only to be read again for MMA. Okay, no, so I guess, yeah, this is the part where it's saying basically the quantization, online quantization, dynamically computing the scaling factors. You have to do the actual, it requires like two steps, converting it and then reading it again to do the actual MMA instruction, the matmul. And what they're saying is that it would be nice if they could integrate this into TMA, which is like a specific hardware component on NVIDIA hardware that handles like async memory movement, essentially, from HBM to on-chip memory. And it'd be nice if basically in one step it could compute the scaling factors, perform the conversion, and on its way, from HBM to TMA, then to on-chip memory like SRAM or registers, in one single fused operation. So you don't have to do, you can cut out like 50% of the data movement basically, by saving a trip to HBM and back. Support for transposed gem operations. This is what I was talking about a second ago. I got confused. So basically they're saying in our forward pass activations are quantized into 1 by 128 FP8 tiles and stored. The backward pass, the matrix needs to be read out, dequantized, transposed, requantized into 128 by 1, so like a row vector now, and stored to HBM. So they would recommend basically future chips be able to do like a direct transposed read before an MMA, so that they can avoid a bunch of these like intermediate steps here. Cool. Yeah, I know that was a lot. So that was basically everything I wanted to cover. Obviously, you can see it goes on for like another bazillion pages, and there's like a bunch of appendices, which I'm not going to cover, because yeah, we simply do not have the time. So yeah, with that, I will conclude. If anybody has any comments, any questions, please feel free to jump in. If I said anything wrong, please tell me. I would really appreciate that because there was some pretty tricky concepts in this paper that were new to me. So yeah. All right, well, if there's no questions, I guess everybody's happy with just passively consuming the content today. I'm happy with that as well. I know it was a lot. I should have maybe stopped for questions or comments intermittently, but I was afraid it would take like 3 hours to get through all this if I kept stopping. So yeah, I'll remember that for next time. Anyways, yeah, this was a pretty awesome paper. The amount of like crazy optimizations that I've never seen before that they did. I can't imagine like the amount of time it would take to implement some of this stuff, like all the like dynamically changing the computational patterns that are being done between each training step and all that. All the PTX code they wrote. I don't know. They're pretty hardcore, and it's a pretty small team, so they must be working overtime on this, like pretty crazy hours, or they're just way more efficient than I am at working. So yeah, cool. With that, I guess I will stop the recording and we can wrap up.